Okay, carrying right on, we fit in nonlinear functions. We've seen polynomials. We're going to now move on to splines, which are more flexible and offer us a wider scope of possibilities than polynomials. So we've got lots of nice built-in tools in R for fitting splines. We're going to look at cubic splines. We need to load the package for splines, which is called Splines, and now we're ready to go. So we'll start off, we'll fit a linear model using wage again, same data as we used before, and we'll fit a cubic spline with knots at 25, 40, and 60. Okay, so let's just do it, and we'll produce the plot. Okay. And we'll put in the knots. So there it is. So let me remind you what this means. So a spline is a cubic polynomial because the function bs by default gives you a basis for cubic polynomials. Here are the knots. So these are places of discontinuity, but they're just discontinuity in the third derivative. So what these are, these splines, again, they're cubic polynomials in each of the regions, but they're constrained to be continuous at the knots, and they're constrained to have continuous first and second derivatives, which makes them really smooth. In fact, so smooth that the human eye cannot detect the discontinuity there. They're discontinuous in the third derivative. So the idea of splines is that they're more local than polynomials. So they don't have quite the wagging tails of polynomials, and they're a nice way of fitting flexible functions. And here we've actually specified where the knots are. And in R, it's really easy to do. There's a BS function which generates the basis, and there's a number of ways of specifying the flexibility and how you place the knots. So one step up from what we called fixed knot regression splines are smoothing splines. Smoothing splines are convenient because they have essentially knots everywhere and they control how smooth the function is with a roughness penalty. And here's our call to smooth.spline. It doesn't use a formula language. It just tells it we tell it the predictor is age, the response is wage, and here we say we want 16 degrees of freedom, and we'll add the fitted function to the plot. So 16 degrees of freedom is rather a lot, and you can see it's picked up some wiggles here. So this is the effective degrees of freedoms of the smoothing spline. So it's allowing quite a little bit of wiggling, and it's maybe a little bit too wiggly in this case. Alternatively, with smooth.spline, you can use leave one out cross-validation to determine the smoothing parameter. If you recall in the text, smoothing splines had a roughness parameter which controlled how rough the function was, and here in this first call we controlled it by specifying the effective degrees of freedom, and the roughness penalty was chosen accordingly. Here we're going to tell it to use cross-validation to pick the tuning parameter, or the roughness parameter. And so there we go. There was a little warning from smooth.spline. It noticed that there were a lot of ties in X, but it turns out that's fine for our purposes, and so there's nothing to be concerned about. And we'll include that fitted function. Well, they all look the same. You have to really zoom in if you want to see any differences. The one that smoothing spline produced had less effective degrees of freedom. It says 6.79. Remember, the effective degrees of freedom don't have to be an integer. It's a heuristic for how rough the function is. And in this case, about 6 to 7 degrees of freedom. Our fixed knot regression spline, let's see, where is it? That's in fit. Oh, we've overwritten fit. Let's see how many degrees of freedom in this one. We'll refit it, and we'll do summary of fit. and we can just count the parameters. And we'll see there's 1, 2, 3, 4, 5, 6 parameters. So it's got 6 degrees of freedom. So with 4 knots, it ended up with 6 degrees of freedom, and the smoothing spline, using a slightly different methodology, ended up with just over 6 degrees of freedom. Okay. Well, the final topic is going to be generalized additive models. We really want to fit a model with just one single predictor. We usually have more than one predictor. So we need a way of mixing these together and also producing nice plots. And the GAM package is going to help us do that. So again, we require GAM. So the GAM package is loaded. And again, we'll use the wage data. And here we'll fit a generalized additive model. So we call GAM, we tell it the response is wage, and here we tell it we want a smooth term in age with 4 degrees of freedom, a smooth term in year with 4 degrees of freedom. Education's a factor variable, so we just say we'll have education in as linear terms. It'll make dummy variables for each of the levels and fit constants, and we tell it the data is wage. Now, this S is a special function known to GAM, and what it tells GAM is it wants a smoothing spline in the variable age with 4 degrees of freedom, and likewise for this term over here. And these two terms are going to be fit jointly, and we'll see when we produce the plot. So before we plot, we'll set up a plotting grid where we want 3 columns. And this may be a little squashed. Let's see. And I'll first plot it and see. Yeah, it's a little squashed. So let's just squash it down a little bit so the plot looks a little bit more balanced. Still, we can squash it down a bit further. No, is it? Yeah, there we go. And what this plot function's done is produce a plot for each of the terms in the GAM, and plotted those terms plus the standard errors for each of those terms. So this is the shape we've been seeing for the variable age in all the univariate plots. But now we've got year as well as education included as well. And so we see that salary tends to increase with year. There seems to have been a dip around 2005, but then continued to rise. And no big surprise, salary increases monotonically with education. Now, because we've limited in plot space here, normally the plot for a factor variable like this would indicate at the top of the plot what each of the levels are, but there's no room for that, and so it's only ended up putting the lowest one. But these are the levels of age, and they're monotone in the amount of education. So this is a very convenient. So this was done using plot.gam. So this is a very convenient way of fitting nonlinear functions in several variables and having nice ways of producing plots. GAM also works for logistic regression and other kinds of generalized linear models. So here we'll use our binary variable for wage, and we'll fit a smooth term in age and a smooth term in year. And so we do that, and we can plot that GAM as well. Oh, plus education, and we plot that GAM as well. We left off the standard errors here because I happen to know that some of them are really wide, and they would have dwarfed the plots. And so this is plotting the contributions to the logit of the probability, each as the separate functions, since the model is additive in those. So you can, using GAM, you can do some tests. So let's see if we need a nonlinear term for the variable year. So we'll fit another GAM where instead of having a smooth term in year, we'll just have a linear term in year. The rest is the same. We'll call that GAM 2A. And now we can use ANOVA to test those two models. And it gives you the two models, and it does the test, and the chi-squares, the p-value is 0.82, which says we really don't need this nonlinear term for year, a linear term will be fine. You can, in fact, test further and see if you need a term at all for year. So we've seen GAM knows how to plot functions nicely. It turns out you can use the plot method from GAM to plot models even fit by LM and GLM. And so we'll demonstrate that now. So here we'll fit a linear model, again with wage as a response, but instead of using GAM, we'll just fit LM, and we'll generate a spline basis using our other spline function, which is NS, which, remember, we had natural splines, and NS gives us a basis in natural splines. So we want a natural spline in age, and here we specify, instead of the knots, we specify the effective degrees of freedom. So this looks very similar to the call to GAM, except we're using a fixed basis, a reduced set of basis functions to represent the splines. And likewise for year, and then plus a linear term in education. So we fit that model. And now, even though it's an LM, we can use the plot method for GAM. Now, since LM's not of class GAM, we need to write out plot.gam to specify that we want to use that particular plot method. And we plot that function. And it does a similar thing to what it did for a legitimate GAM object. It plots a fitted function. And it's included the standard errors. So that's just a glimpse of the capability of the GAM function. Have a look at the help files for GAM. There's documents on GAM. Rob and I actually have a book, a 1991 book on generalized additive models. You can find out lots more details, and there's various papers that have been written on GAMs. And you can also look in the chapter in this introduction to statistical learning to learn a little bit about GAMs and see what the capabilities are.